When we multiply out binomials that are similar but opposite in symmetry, so 1 plus, 1 minus, so here we have x plus 1, x minus 1. So they have opposite symmetry. We end up with an interesting pattern. So if I distribute this out, first times first, I get x squared. So I have here my x squared. I should just write this out. X minus 1, x plus 1. So when I multiply first outside, I get negative 1x. Inside, positive 1x. And last, I get negative times positive, so I get negative 1. So this becomes negative x. This is positive x. Negative 1 times negative 1, or negative 1 times positive 1 gives me the minus 1. So an interesting thing happens here in that we end up with these opposite terms. The like terms that we usually add in the middle, these cancel out. Okay, actually, I should just cancel them out in one group. These are 0 terms, 0 pairs, so I'm going to cancel those out. And I end up with x squared minus 1. So these are special ones. We call these conjugate pairs because they are symmetrical but opposite in symmetry. And they give us a certain pattern. And what ends up happening with these is the middle terms always end up canceling out. So we end up with a square minus a square. So because of this opposite symmetry, this term and this term here, they are opposite and they cancel out. So these are special, and we call these difference of squares because we end up with x times x, or x squared here, and we end up with 1 times 1, which is 1 squared here. And because of the opposite symmetry, we end up with positive and negative, which gives us the negative down here. So this is called the difference of squares. So again, let's multiply this out. We're going to end up with x minus 3, x plus 3. The distribution is going to be x times x, x squared, x times 3, positive 3x, negative 3 times x, so negative 3x, and then negative 3 times positive 3, so we get our square of 9, and it's negative. Again, since we have this opposite symmetry here of negative 3x and positive 3x, these cancel out, and we end up losing those pieces. So we end up with negative 9, and so as we cancel out our 0 pairs, we end up with x squared minus 9. So we end up with the square minus the square, and the square of this term and the square of this term. So it's important to note that when we have this difference of squares, we actually have 2 squares, okay? And we're taking away these 2 squares, and since these two are 0 pairs, they actually don't exist. And it's very important to understand that these are not a square shape. So when we actually try to do the opposite, when we try to factor, okay, or square root, we can't just square root this and say that it's equal to x minus 1 or anything like that, because by definition of square root is taking a square and finding side length. If we don't start with a square, so here we have squared minus squared, these are not, when we put them together, we don't have a square shape. So we cannot square root. So that's important to note that the shape of these are not squares. Okay? In fact, if you think of our length and width, our length is shorter than our width, which means that it must be a rectangle. This is not a square shape. So we cannot square root these terms that when we see these binomial difference of square binomials. Okay, so let's try doing this one again. So this one is, again, our difference of squares, x minus 5 And make sure that you're observing the pattern that's generated here and why we end up with this opposite symmetry giving us 0 pairs. So we're going to multiply x times x times negative 5, so negative 5x. Okay, 5 times x is positive 5x. So that's our positive 5x down here. And then positive times negative, and then we have 5 times 5, so it gives us our negative square. So here again we have our pairs that cancel out. There's our 0 pairs. Okay, we have in our diagram here, we have the opposite symmetry here, so there's our 0 pairs, they disappear. So these two areas cancel out and we end up with 2 squares, and 2 squares together do not make a square. When we put it together, we end up with x squared minus 5 squared. So there's our difference of squares. So even when we have coefficients in front, as long as we have this type of symmetry, okay, we end up with 3x minus 2, 3x plus 2. This opposite symmetry, when we distribute out, we end up with our square, which is 9x squared here. These two terms cancel out because we end up one positive, one negative. So negative 6x, positive 6x. And then 2 times 2 is 4. 2 squared is negative squared. These terms cancel out, so with positive 6x, negative 6x. They are the symmetrical, but they are the opposite symmetry, so that we end up canceling those out. And again, these are the opposite terms. And when we look physically at this shape, when we get rid of these are 2 squares, and 2 squares do not make a square shape. So whenever we multiply out these conjugate pairs, these are called conjugate pairs, when we have the same symmetry but opposite, the middle terms always cancel out and we get a difference of squares. So we end up with this as the first term squared minus the second term squared. So this is a result of multiplying conjugate pairs with this type of symmetry. These middle terms cancel out and we just have these 2 squares left over.